Okay, so the first question, can you read this?
Yes.
Okay, so this is the preprint on archive of Markl and mine, where you can find the results which I'm going to talk about. So let me start with some very classical things. So I believe that everyone knows the original definition of operad by Peter May, I think from 1972. So what operad was, it was a collection. Well, I will not be very careful about the rank of this n, and Pn were object of some symmetric monoidal category, but you can, I'm going completely to suppress this P during my talk, and you can think of vector spaces, for instance, if you want. And what was important that the structure operation of such a operad were something like maps that went like this: Pn1 times Pn2 times Pnk into Pn1 plus Nk. Well, and of course they had to satisfy some assumption, associativity, and the equivariance with respect to group action, if there is any present. And there is also assumption of the existence of unit, but it is actually not necessary. So we can also think about non-unital operads. So my favorite way how to visualize these kind of operation is this. So I have the triangles which symbolize the operations. I am thinking of this way of composition. So this fellow has k inputs, this fellow has n1, n2, and k inputs, and the result is something which has this number of inputs, n1 plus nk. All right, so this is Peter May's definition of operad. And later on, in 1996, I introduced another, let's say, version of definition of operad, which was based on circle I operations, which were the maps from Pm times Pn into Pm plus n minus 1, where I is between 1 and n. And again, I think of this operation as something that takes the first element from here and into the input I insert the second element. So it has m input, it has n inputs, and the result is something that has m plus n minus 1 inputs. So why I did so? The main motivation why I came up with this definition was that free operads in this setup are more structured, namely they are naturally graded by number of operations which are applied on generators. Let me try to draw a picture that I believe explains so. So as everyone knows, free operads are, or elements of free operads are represented by trees with vertices labeled or decorated by generators. So you may think of this tree as something representing element of free operad on some collection of not important which one, on 8 inputs. And there are 2 ways how to construct it using May's definition. So you can, oh, this is not it. So you can apply gamma here, and then you can apply gamma like this. So you did so using gamma twice, or you can do it differently. You can first take gamma here, and the result insert to the top. So you applied gamma 3 times. On the other hand, the number of circle eyes, if you use my definition, is the number of internal edges, which is in this case, I believe 6. All right. So this was a big advantage because I wanted to talk about quadratic, binary quadratic operads, and so on and so on. As actually Ginsburg and Caprano they did in their seminal paper, but I somehow wanted it to be more structured. So this was my solution. So this was the first motivation. Another motivation was that in this setup, the structure operations are binary, so it has 2 inputs, and also the axioms are the associativities are binary, which means that all these stuff behaves like, let's say, associative algebras or algebraic objects we are used to work with. And what became even more important much later is that in this setup, operads themselves are algebras over, say, hyperopera, which is binary, quadratic, and causal, as was established quite recently. All right. And let me make 2 remarks on history of all this stuff. The notation circle I is not my original. I was inspired by a paper by Gerstenhaber, I think, from the 60s on deformation theory of associative algebras, where he used this notation for composition of multilinear maps. And another, which kind of relates to the title of my talk, when I published the paper where I introduced this notation or this setup, I got kind of agitated, I would even say angry email from Peter May, who said that I am not supposed to use this because it completely obscures the nature of operads, and that he's going to ignore everything which is based on this notation. I was 36 by that time, so you can imagine how I felt. So I must say that I am very happy that nowadays, I would say for most people, this is the definition, namely for newcomers, it may even be the definition of operads, which completely kind of took over May's approach. Very good. Everything is clear so far?
Sure.
Yeah. So let me make some comments. So we are still in very classical setup. Let me make some comments about relations between these 2 definitions. So what I'm going to write is that under some very standard assumptions, for instance, under the presence of the unit, those definitions are equivalent, and I'm going to indicate the proof, which is very elementary, but which somehow will be used in the second part of my talk, which will address operatic categories. So this is a, let me call it theorem, not because the proof is difficult, but because it's kind of important. So there is the following natural inclusion of categories. So the category of Markov's operad is a subcategory of May's operad, non-full full subcategory. And so this is the first part of the theorem. And second, if restricted to unital, it is the categories are isomorphisms. Fine. So what about the proof? What about the proof? So how I construct this? So suppose that I have my operad and I wish to present it in a May's form, meaning I have circle operations I like to do to define gammas in the sense of May. So of course I'll do it in a very explicit and small example where I wish to define this May's kind of thing for this type of composition. All right. And I define it in the following way. Let me draw the picture. So, and then make some comments. All right. Okay, what else? Fine. So this is X, this is A, this is B, and this is C. So I have circle 1, circle 3. Here I have circle 2. Here I have a circle 1. So I don't think it is necessary to write it in terms of elements because it's obvious what I mean. So this is the way how out of my circle I operations to get gammas in sense of Peter May. Right? So what about the opposite direction? So I need to define circle I using May's gammas. So I want to say what this is, X and I. Yeah, and what I do, well, I take the following gamma composition using the unit. So on the position I of X, I put A, and to remaining positions, I put unit. So this shows how units are important in the isomorphism part of the theorem. All right, I can again write it in elements, but I don't think it will be.
Martin, I have a question.
Yeah.
Why is it full subcategory without unit?
Where is it? What? Use of categories without units.
You said no. You said that this is a full subcategory.
Yeah. Yeah.
Even if there are no units. Why is it so?
Yeah, I guess so. It has less objects, but well, I need to think about it. Well,
okay. No,
yeah,
no.
I somehow expect it as a full subcategory, but
your morphisms are just maps of collections with respect to compositions. So you get all.
Well, it could be expected, but well, let's put it down to the carpet for the moment. So maybe it's good to give some example of something of operad which belongs to which is May and which is not mine. Oh, by the way, I somehow misunderstood your question. I thought that you were asking what is the use of operads without the units. And they are natural examples like modular operad of stable surfaces, because there is nothing in arity P1 in arity 1 in genus 0. So this is a natural example of operad without unit. So they are examples. But let me show you example of operad which is may, but which doesn't come from my operad. And this is kind of exercise. So I define Pn is well, I'm in vector spaces, so it is K ground field if n is 2 or 4, and it is trivial vector space otherwise. Yeah, and the only operation which is not trivial is may is gamma, which goes this way 4, and all these things are ground fields by definition, and it is declared to be the identity, the natural isomorphism. And I leave as an exercise to prove or to verify that such an operad doesn't come from any operad of my type. Very good. So this is traditional stuff. Let me move to operatic categories and operads over operatic categories. So I do believe that you already heard about the notion of operatic category. I'll recall some basic features of this notion and give you some actually two very explicit examples. So I believe that you get some feeling how it works. So operatic category. It is a category O, which is equipped with a functor, which we call cardinality functor, into fin, which is a skeletal category of finite sets. And it has the following extra structure. Each morphism in O has a fibers. So for each F, there exist objects, well, Fi, which I also sometimes denote as F inverse I, where I is from the cardinality of what, of T. So for instance, if cardinality of T is 1 up to K, then I have F1, Fk fibers, and we introduced, by we I mean Markl and me, we introduced a shorthand for this by writing following thing, which I don't know how to read, but anyway. S. So this symbol means that F has a fibers F1 up to Fk. And I have to emphasize that despite this notation, it doesn't mean that Fi is the inverse of I. It doesn't even make sense. The types are wrong in general. So there are some objects of a category, and of course some conditions must be satisfied. So this is the first piece of data, and the second piece of data is a choice of local terminal object. So in each component, C of O, I choose a chosen local terminal object. So they may be several, of course, isomorphic local terminals, but the choice of a preferred ones is a part of structure of operatic category. And of course, I'm going to give you example right now. Interesting. Maybe I can lift it a little bit. Well, it's still readable.
Yes, yes.
Very good. Oh, but maybe I'll continue on this board anyway.
So here, big Fi is an object of O, right?
Not what?
The fiber Fi, it's an object of O.
It's object of O, yeah. And you will see very explicit example. The first one, the first example of operatic category is kind of well, not very surprising and not very deep, but well, I will use it anyway because it's related to the classical stuff, which I start with. So where is it? Okay, so the example of operatic category, the first one is category delta, which is a skeletal category of finite ordinals and order preserving maps. So for me, well, I choose a special choice of representative isomorphism classes, namely something which I denote by an online, and this is the ordered set like this, and is a natural number, and the maps are order preserving maps of these fellows. So, well, the example 1, 2, 3, 4, 5, 6, 7, 1, 2. So this is 7, this is 2 online, and the map may be something like this. So the first 4 elements are taken to first element of 2 and remaining to the second one. So this is example of F, and fibers are here. So this is the first fiber, which is clearly for online, and of course the position of these fellows are 5, 6, 7, but we have to take representative. So actually the second fiber is of course 3 online. So these are fibers. These are the fibers. So F inverse 1 is, yeah, I didn't say what cardinality is. The cardinality is defined in the obvious way. So the inverse, the fiber over 1 is 4, the fiber over 2 is 3, and I
Are
can.
your maps surjective?
No, I didn't require it. No.
But you don't have empty set, right? You don't have 0.
I may have empty sets, or I may assume that the maps are subjective. So it is kind of ideological, but although correct example. So if I wish to say in some more refined manner what the fibers are, so what is fiber of F? Yeah, it's just to answer your question. If I wish to allow empty sets, I take this algebraic extension of delta, and everything will be all right. Okay, so what is the fiber of such a map over I? So I take a map here that takes 1 into I here, and then F minus F inverse over I, which is fiber, so it's not inverse of it's fiber over I, is defined as a pullback of this diagram. So this is example of category where fibers are pullbacks, which is something which was considered by Barrick, and he called it, I guess, operator category, but it needn't be the case. They are actually typical examples where so the fibers are not pullbacks. Very well. So this is the example of operatic category, and I wish also to speak about operads in operatic category. So what are operads? They are collections indexed by objects of O, again, in values in some symmetric monoidal category, and they should have also some structure maps. So for any, okay, I'll use the shorthand. So I have a map in O from S to T with fibers F1 up to Fk, and to each such a map, I have a operation gamma F that goes from PT times P F1 times P Fk into PS. Yeah, and I also have a unit, or if I wish to have units, I have a notion of unit, and the notion of unit requires that for any C, which is a connected component of O, I'm given map eta C, which goes from okay, I wrote it as a K, but it is monoidal unit of V in general, and it goes to the value of P at the chosen representative of this connected component. So these are units, these are structure operations, and of course, some axioms which I'm going to ignore, not mention explicitly, are to be satisfied. And this was introduced by Markl and me, although the main idea belongs to Markl by all means. But I'll call it just for the purpose of my talk as a May operad in operatic category, because it uses this kind of operations where everything is being composed at one go, in one go. Fine. So what about example?
So this is like the May version, May definition in operatic category.
Yeah, and this was actually the original definition which we used in our paper, where operatic categories were introduced on Darim conjecture. Yeah.
But there will be a Markl one afterwards.
There is going to be another one, of course. Very good. So example. So what the operad in this category delta is? So I have to have some Pn for any object of delta. Maybe it's not very visible now. So of course, to make notation closer to what people are used to work with, I will denote it just by Pn. And so what about the structure operation? So let me just recall once again. Is it? It's kind of frozen, I guess.
We can hear you, but the image is frozen, yes. I think we lost Martin. Martin, are you here? I mean, you're back. You're back.
Yeah, I'm back fine. So
you're back from Prague. Great.
Yeah. Okay. So it's all right. So
It works.
It works. So you got this definition of operator in operatic
Ah,
category?
yeah. It was just frozen for 10 seconds, no more.
For 10 seconds. Very good. So now I'm going to analyze what operads for the category delta are, and I was going to recall this picture, which you can still remember. So what are the fibers? This is S in the notation for definition of operad. This is my F, and these are the fibers. So the structure operation gamma F should go from P2 times P4 times P3 into P7. So it has a shape of maze operation in a operad. And indeed, it turns out that operads for delta are non-symmetric operads in main take. Very good. So I wish to understand it, the notion of Markl operad in this more general setup. So what are circle I doing? Once again, so example may be something like I have 4 inputs or 5 inputs, 1, 2, 3, 4, 5, and at input number 3, I insert something with 3 inputs, 1, 2, 3, and this is going to be my circle I. And well, if I want to define it using maze operations, I need to put units to the remaining places. But anyway, it is related to gamma F, where F in this case is 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. And 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And this is, I guess, my F. Okay, so this is F. So what is kind of what makes this this type of maps? What singles them out? That all fibers except the precisely one, are trivial. Namely, they are the chosen terminal objects, which in case of delta, so I didn't say what chosen terminals are it's precisely one. There is one component of connectivity, and I choose the one as a chosen terminal. So all fibers are chosen terminal except precisely one. So if I wish to seek a version of my definition for operads in operatic categories or over operatic categories, I have to use this type of maps. So let me formulate a provisional definition. Provisional definition is I say that the map F is elementary if all fibers of F are chosen terminal except precisely one. let's say F, and I will denote the situation by writing the solid triangle. So one would expect that my operads over operatic categories will have structure operations parameterized by elementary maps in this sense. In the minute we will see that there is still something which is not correct on this definition. So I'm going to improve the definition in the moment. Okay. All right. So let me erase the board. So I'm going to introduce the category of directed graphs, which is very important because it has various versions or clones which are related to the most common operatic or probe-like structures. So this is defined in the following way. All right, so category GR of directed graphs.
Martin, we cannot see the very top of the board. Just
Yeah.
we can't see. Thank you.
Well, maybe I can lift a little bit the camera.
We can't see it now. Yes. Perfect.
So so what this directed means, these are graphs in the common sense, such that they are equipped with linear order of vertices. They are equipped with located orders of half edges adjacent to each vertex. So don't panic, I prepared a very nice picture. I believe it explains it. And moreover, there is a order of legs. Okay, so now I'll try to move camera.
Martin,
Did
you mean ordered graph or directed graph? Because now papers.
Yeah, I think that we said
Directed was where there are directions of edges, orientations.
so. We call it ordered graph, right? We call it ordered graph after all. We kind of mix these two things up. But
Yeah, that's a little
I believe that in the final version we somehow got control of terminology. So I'm very sorry. It's actually ordered. Thank you. Ordered graphs. So everything is ordered. And here goes the picture. So this is what I was working on before my talk. So you see the graph. It may have double edges. It may have loops. It has legs. And so, as I say, the vertices are ordered 1, 2, 3, 4, 5. The half edges at each vertex are ordered 2, 3, 1, 4. The legs are ordered also 1, 2, 3, 4. That's it. So notice that if I'm given the order of vertices and the order of half edges adjacent to each vertex, I'll call these orders local orders. it is the same as to give, well, it induces lexicographic order on all half edges. So these goes first, these goes at the second, and so on. So, and I am not sure if I am going to use this correspondence, but this is the other way how to say what is the order of half edges. And what are the maps? So the maps are the maps of graphs by which, at least in this first kind of informal introduction, I mean contractions of subgraphs and reordering of the things which I've ordered. But with the provision that the global orders, by global order, I mean the order of the legs, is fixed. So this F should be example of such a morphism where I contract this subgraph and the contraction goes to vertex 1 here, and here I contract this subgraph and the result goes, the contraction goes to vertex 2. Well. So these are directed graphs. I'll try to use some board, some place here. So what is the cardinality functor? So cardinality functor assigns to gamma the set of vertices of gamma. So cardinality of this graph is 5. Cardinality of this graph is 2. Fine. So, and how fibers are described? So the fiber, I prepared example of fiber over 2. Fiber is, as a graph, the subgraph that has been contracted. But what makes this construction somehow subtle and meaningful is that, of course, I have to say what the local orders are, what the global orders are, and what are the order of vertices. So the orders of vertices are obtained from the graph that has been contracted. So, for instance, because I am in skeletal category, I didn't put the orders here. So this is 2, which is the smallest one, so it is the first. This is 3, which is the second, and this is 3. So this is how I get order of vertices. The local orders are also borrowed from the subgraph that was contracted, which means that, for instance, the local order of this vertex, which corresponds to this one, is the same. So if I made no mistake, it should be all right here. But what is subtle is the global order. And the global order is borrowed from local orders of half edges adjacent to the vertex to which the graph was contracted. So if you somehow think a little bit about the picture, you will realize that this edge corresponds to this one, this to this one, this to this one, and finally this to this one, which means that this, which is here, actually this one has to have one, has to get global, I mean, the first in the global order, and so on. So 3, 4, and 2. So this is very subtle thing, and I think, and I spent so much time explaining so because it is indeed the thing which makes everything working, and we spent, I mean, me and Markl, quite a long time to figure out all the subtleties of these things. So this is category gr and morphisms. So what about the local terminal objects? So local terminal objects are corollas. So what is directed or the pre-ordered corolla? So it is corolla, as everyone would expect. So it is corolla. It has some global order, 1, 2, 3, up to n. And it also has a local orders, which are described by some permutations, sigma 1, sigma 2, sigma 3, sigma 4, sigma n. So let me denote it by Cn sigma, where sigma is from sigma n. So these are local terminal objects, and I declare that chosen are C and where sigma is identity. So for instance, 1, 2, 3, 1, 2, 3 is a chosen one, while 1, 2, 3, 1, 3, 2 is not a chosen one, but it is still a local terminal object in the same component. So actually these two things are isomorphic, but I declare only this one to be a chosen one. Yeah, the other way. Thank you. So this, okay, so this is not a chosen one. And let me just state a theorem which okay, which says that algebras for terminal gr opera for terminal gr operad are modular operads. Well, without the genus grading, but it's not so important. Because also I didn't say what algebras are, but this is what makes them important. And by modifying this category of graphs, you can get operads describing other types of important structures. Very, very well. So what may be the notion of my operad in this context? So before I come to that, I'll make a little exercise. So I had this corollas on the board a minute ago. So I have a corolla with n, whatever spikes, with local order sigma, and I have another corolla with the same number of spikes and local order tau. And since it is local terminal, there is only precisely one mat. And as an exercise, I'll let you to prove that fiber of this fellow is the unique fiber of this fellow is corolla with a local order tau inverse sigma. Yeah, and if I make a substitution, because it doesn't look much very intelligent, if I make substitution that instead of tau, well, instead of sigma, I will write tau lambda, then I'll get the diagram Cn lambda, which is fiber of Cn tau lambda, which goes to C and tau. And if you still remember structure operations of May's operad, what I get here, that the structure operation corresponding to this unique map between local terminals is the something which goes from M, which M is this the operad over G, C and lambda times okay, actually it was tau, but it is not so very much important. M, C and lambda, and it goes to M, C, tau lambda, the same and everywhere. And well, if you expand the axioms, you'll find out that what you get here is actually graded or sigma n graded associative algebra. I believe the notion of sigma and grading is obvious, and it has to be compared to P1 of a traditional operad, which is associative algebra or associative monoid. Very good. Notice also, coming back to my provisional definition of elementary map, that this map has the only fiber, namely this one, and it is elementary if and only if tau is sigma inverse. Which means that if this condition is not satisfied and this map is not elementary, therefore, during to my provisional definition of elementary maps, I mean, the fiber is not chosen one. So due to my provisional definition of elementary map, this diagram should represent an elementary map. So the structure operations of my operad should involve also this type of maps. But I don't want so. I want this because notice, for instance, that there is an infinite number of compositions of infinite length of these type of maps. They are kind of important and potent, so they cannot be. There is no hope that they will induce some reasonable filtration of free objects, which was what I was after. Therefore, I have to slightly modify the naive definition of elementary maps. And this is what I'm going right now. So let me just use the remaining piece of this board. And the thing which does it is the notion of grading. The notion of grading, I say that the map or function map of sets from objects of all, well, it may not be a set, but anyway, from objects of O into natural numbers is a grading if for any f, okay, I will use the notation. So f has a fibers f1, fk, s, e. So for any f like this, I have the following equation: plus e f1 plus e f k is es. So this is the notion of grading. So examples. Okay, let me again erase, or maybe I can use this board also. So examples, delta is graded by graded of n on line is n-1, example number 1, and example number 2, gr is graded by E gamma is the number of internal edges which was actually the reason for this notation E. For this notation E, and so this has a very good flavor because as I wish to my circle I operations, my would-be circle operations, to describe or to be related with contractions of graphs which contract at least one edge. I don't wish to have them connected or parameterized by isomorphisms like this, like isomorphism between local terminal objects. I wish them to do something visible and non-trivial. And actually, this leads to the following final and correct definition of elementary map. So I say that this is definition. The map phi from S to T in O is elementary. Is elementary if all fibers are chosen terminal except F such that the grading of F is like this. Well, it can be very easily shown using the property of defining property of grading that if U is local terminal, then yeah.
So what about the underlying patch? Would it be order preserving? If you take the arity of the map.
Very good. It has to be order preserving, but I'm, as I say, I'm ignoring some subtleties. I'm ignoring some subtleties. Well, Dominic was absolutely correct that I need to. So in my definition of elementary map, and thank you for mentioning it, I wish to, maybe I oversimplified everything, that phi, which is the map of ordered finite ordinals, must be order preserving. Order preserving. Well, at this level of, let's say, precision, I cannot explain. I'm unable to explain why this condition is also necessary. But this condition excluded because of this property, which follows from definition from properties of grading, excludes the map between local terminal objects. So in category of graphs, it indeed means that my elementary morphism contracts at least one edge of a graph. And then let me formulate finally the definition of my operad in general operatic category. So as I explained, we need to assume that O is graded. So O is graded. Assume O is graded. Then Markl operad is perceived from all isos, which is a subcategory of isomorphisms. So it is perceived with values in V in symmetry monoidal category. So by the way, this shows that this is a collection indexed by objects of O, and I have an action of isomorphism, which is precisely to build the isomorphism between local terminal objects somehow built in the definition of morphism. It has to be compared to the action of symmetry group in classical setup of operads. So this is what is it, and what is a structure? What are structural operations for any elementary? Let me use this notation. I have some circle P, which goes as can be expected from NP times MF into MF. So actually, I don't know how long the talk is supposed to be.
1 hour.
1 hour. Okay, so that's it. Thank you very much.
Thank you, Martin.
Maybe I can also add one thing that,
Yeah, sure.
as in the classical case, we have a theorem saying that if some conditions both on the operatic category, this is important, they are operatic categories for which there is no equivalence of categories of May's and my Markl operads. So some conditions both on unlike operatic category and on operads, something like one connectivity. So when these conditions are satisfied, the categories are isomorphic between Markl and May operad. Okay, thank you.
Thank you very much. Is there any further question? Feel free to ask, please.
Maybe a short question about what you've talked so far. In the category of graphs, is there only surjective maps, or you also allow injective maps?
I'm not sure if there is notion of surjective.
I mean,
what is a surjective map of graphs? I don't know, but
okay.
I mean, it is certainly not embedding of subgraph.
Okay, yeah. You only consider morphisms where you contract something, right?
Yes, or reorder, local reorders, or global
Okay.
reorders, but certainly only contraction.
Okay, and your isos here would be reorderings.
Yeah, you can say so.
Okay, thank you.
Yes, Victor, ask your question.
First, thank you very much for your nice talk, Martin.
Mm-hmm.
I'm wondering about the relation between your operatic categories and the operator categories of May and Barwick. You know their work.
Yeah.
Is there any connection between both notions?
I'm sure that Michael is more qualified than me to answer this question, but I believe that the difference is something like Barwick categories or operatic categories, such that the fibers are pullbacks are the same as Barwick categories, modulo some details. Michael, is it so, or
Yeah. That's absolutely correct. It's Barwick operators category is a subcategory of our operatic categories. So this is true. Full subcategory.
I can give a very simple example of categories, operatic categories, such that fibers are not pullbacks, but I'm running out of my time. So I believe the examples can be found in the preprint which I mentioned at the beginning of my talk.
Okay, thanks.
Is there any other question?
Well, maybe you could say a word about how you speak of causal duality in arbitrary operatic category.
Yeah. So we have a theory, I would say, finished, and we are working on final version of kind of extended version of the preprint, which I mentioned at the beginning of my talk. And there is also another paper, another preprint of Markl, Johanna Operadic, and me, where we prove that assuming the theory has been built up, the operads describing standard things like modulo operads, cyclic operads, ordinary operads are causal, binary, quadratic. Well, I would say this result has been around, has been expected for some time. Certainly, it has a lot of interest in an important application, namely that all these derived mathematics operads, by which I mean cohomology theory, deformation theory, strongly homomorphic version, is kind of simple. And well, I have also to say that there is a recent paper by Ward, Benjamin Ward, that proves that operad describing a model operad is quadratic, binary, causal, but Ward is using different language. I would say kind of, I would like to say obsolete, but based on colored operads with the with arities in groupoids. So this is something very, very classical. So you can say very easily what such operad is, but the machinery, the techniques which you have to master to prove the result is very involved. While in our setup, which I think is advantage, you have to do a lot of preliminary work, but the presentation, quadratic presentation of the operads which I mentioned, or model operads, for instance, is very, very simple. It can be done in 2 pictures, which again could be found in the preprint which I mentioned at the beginning.
If I may, Martin, I would not say that groupoid colored operad are, I don't know, old-fashioned classical blah blah blah. This is quite new.
Well, okay.
So it was introduced by Petersen and then further developed by Ward. And what Ward has been doing is very interesting. I don't want to say that it is obsolete. I mean, it's developing massive products for graph homology with this technology. So as you said, it's very important and crucial to prove that whatever guy controls, for instance, modular operad is causal, because then you have all the results about homotopy, modular operads, and depth theory, etc. So this is what is used in cohomological field theories, for instance, or graph homology. So
yeah, and of course I have also to mention your absolutely interesting paper about the classical operad, where you resolve also the action of symmetric groups, while somehow these actions are built in this language. So
yeah. But I think what I would be very much interested in is it seems lurking behind Ward's proof, which takes a few pages indeed, is it seems to be the contractability of some kind of polytopes encoding the theory. You know, for associative algebras, we have the Stashev polytopes. For operads, we have graph polytopes of Cardovados, etc. It seems that lurking behind the proof of Ward, there is ultimately a contractibility of a polytope which encodes the notion. So is it the case in your theory?
Absolutely. So in this paper by Johanna Operadic, these polytopes are explicitly constructed.
But do I remember well, for instance, for operads, you have the polytope of non-symmetric operads. You also have a polytope for symmetric operads?
Yeah, I hope so, yeah.
Okay, good.
This is general construction somehow. There was another group of computer scientists, I would say, that had some algorithm to construct polytopes, and the paper is the combination of this algorithm. Well, actually, in a sense, the history repeats, because Jim Stashev told me that associahedra were also invented independently by someone else, by some category.
By Tamari, but Tamari.
Yeah, but okay, fine. I don't remember names, but again, kind of connection of 2 different approaches. place.
Okay, thank you very much. Is there any other question?
Can I comment a little bit again about this notion of operads with groupoid scalars? So of course it's not obsolete, it's maybe not a good word, but what I want to say is that this paper of Peterson, as far as I know, is 2011.
14, I would say, but
or 2009, I don't
it's
remember.
less than 10 years. So
Yeah, but there is a paper of Dan Street about substitute, and where this is 2004, and
right.
everything was defined there, in fact. But it's more generality, because Peterson asked about examples of his notion in which actually cat, not in groupoid. But this is notion of substitute. It's much before. It's exactly the same notion.
Thank you very much. Yeah, I didn't know about that. But we should not say obsolete. I mean, it's working perfectly well, and in
a sense, yes, it's also Also, you have to remember Ezra Gesser, Operad revisited.
Yeah.
He defined actually the same notion.
Yeah. So
I wish to take back the word obsolete. By that I meant that it's kind of the direct continuation of classical approach on operads. It's classical, maybe I would say classical or traditional rather than obsolete.
Sure, classical. Yeah. Well, good. Thank you. Okay, so
may I ask a last question?
Sure.
Okay. So in the introduction of your paper, you take an operatic category, you do the plus construction on it, and then you take the terminal operad 1 O plus. And you claim that this terminal operad is always causal autodual, the causal self-dual.
It was kind of conjecture that plus construction improves. We never prove it, I guess, but
okay. So it's not in the paper, but maybe in your forthcoming.
Well, the reason for this hope was that the structure of O plus very much resembles non-symmetric free opera. But, so again, there may be some polyhedra hidden behind, but we hadn't proved it. We just noticed that in all examples we know it happens.
Okay. Thank you.
It's just also because plus construction is based on trees, and everything which is based on trees, all examples are clearly self-dual, and that of course was a conjecture. But we did not prove it in full generality, of course. But we have strong suspicions that it's true.
Maybe it's because you have the opetopes lying behind.
That's true. That's what I say. It's based on trees, and opetopes are sort of generalized trees. And that's what you do when you construct plus construction. You use trees, and once you use trees, it's kind of self-duality. It's almost there. When you have general graphs, you cannot expect this because you have more complicated picture. But for trees, it's the same proof as for ordinary opera, more or less.
Yes, but the plus construction, you can apply it to graphs as well.
Yes, you can apply for graphs, and then you get what Martin mentioned as hyper-operads, as operads for plus construction over graphs, etc., etc. But but it will be with the graphs with nestings, right? Yeah, so we can continue with this. But this will be like tree-looking graphs because nestings are like trees.
And again, this is quite explicitly at least some instance of this described in this paper by Markl, Jovana, and me. You have these trees whose vertices are indexed by graphs.
Yeah, there's
kind of compatibility involved.
Precisely. Yeah.
Okay, is there any other question or comment? We had a lot, it was good. So if not, I propose that we thank Martin again for this very nice talk.
Yeah, thank you very much. And I believe that we'll meet in some other times.